Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, I think we'll get started. We're excited to have Emma Brunskill here again. She visited us maybe, 8-9 months ago?
Yeah,
for a talk, and is now actually interviewing for positions around the country. We hope to impress her with Microsoft Research as being an interesting platform and a promising one for her future while she's here today and tomorrow. Emma is an NSF mathematical sciences postdoc at UC Berkeley, where she's working with Stuart Russell, an old friend, and others. She did her PhD in computer science at MIT, and before that, she did her master's in neuroscience at Oxford as a Rhodes Scholar, and she's interested in core AI. I think she'd bring to the table some interesting interests in planning under uncertainty, sequential decisions under uncertainty, the POMDP area, human-robot interaction, which is a growing area on our team, and education, as well as information and computing technology for development, which are, I think, two areas that we could use some bolstering in. In particular, education, I think, is very promising. So with that, I'll let Emma take over here on leveraging structure to efficiently make good decisions in an uncertain world. Emma.
Thanks, Eric. I'm really excited to be here, so thanks everyone for coming. I know it's fairly early still in computer science time. So as Eric said, I'm primarily interested in how do we make sequences of related decisions when the outcome of each of those decisions is uncertain in order to achieve a good outcome. And this is known as sequential decision making under uncertainty. For example, you could imagine trying to sequentially select which of a new set of advertisements to display to users, given that you don't know what the click rate is for each of those advertisements. You could also think about how would you compute a strategy for how to harvest a natural resource like fish, where the population of fish changes over time and is hard to observe. This instances of sequential decision making under uncertainty comes up in a wide range of other problems as well. And things like personalized user interfaces, healthcare, and a wide number of other types of applications. I'd also argue that this is really a fundamental challenge in artificial intelligence. So to me, our ability to make sequences of decisions under uncertainty is really a core part of what makes us smart. And so tackling these types of challenges is a core aspect of AI. If we want to make sequences of decisions when part of the world is hidden, and I'll quantify that a little bit more clearly in a moment, these problems are formally hard. They lie in p space or x time, which means that it's going to be very hard for us to solve these type of problems in their full generality. And in fact, most artificial intelligence planners have generally handled very small problems, or fairly small problems. There's obviously some exceptions to that. But part of my inspiration has really been, well, what could we do if we could scale up to enormous problems? What type of things would that enable? And to me, it would enable some really exciting types of applications. So for example, I think we could do things like huge security and surveillance operations over things like where to patrol and when to raise alerts. I think we could create better physician's assistants that would help physicians make decisions over the course of a patient's lifetime in order to make sure that that patient's lifetime maximizes their health and well-being over the course of 50 to 70 years. And I think we could really revolutionize education through the use of personalized tutoring assistants. So my approach to trying to get up to these type of problems is really to leverage structure. And in particular, I've been focusing on how do we pick models that well approximate these type of real-world problems, but also provide us with significant amounts of computational leverage. That has enabled us to scale up to some problems where we couldn't previously achieve good performance. I just want to say a quick word about the approach that I have to these type of problems. The first is that I think that formal performance guarantees are important. And the reason I think that these are particularly important, in addition to being theoretically appealing, is that if we're looking at really large domains, it's going to be impossible for us to simulate all the types of scenarios that might occur. And so in order for us to have confidence in the type of systems we develop, formal performance guarantees can give us some measure of promise and confidence in these type of approaches. The second thing I think is important is to actually do real-world instantiations. I've just told you that the way I'm going to scale up to some of these large problems is by leveraging structure. But the way I'm getting that structure is by being inspired by particular real-world domains. And we need to make sure that the assumptions are actually correct. And so we can only do that by going back into the real world and see whether or not the approaches we develop are actually creating good solutions in those cases. Now, I know for some of you this is going to be a review, but it's a bit of a mixed audience, so I'm just going to briefly do an introduction to Markov decision processes. So a Markov decision process can be specified by a tuple, where S is a set of states. So the state in this case for a sailboat is its location, and the set of states is all the possible locations of the sailboat.
Is this the Jim Gray missing?
It is not. It's actually the spice trader example. That would be sadder.
Actually, when he went missing, if you look at the blog that was created, I did create kind of
a Markov
analysis that I suggested would be the way to triage efforts at the time. So it was
actually.
Don't look for him in the South Indian Ocean.
It was looking at the currents and wind, and then
exactly.
triaging based on that. If people were looking at all these satellite photos, where to start looking.
Right,
I said
locality.
Back then I said that let's condition the fact that he's alive and say, well, given that he's alive, what would you do? Where might he be?
Right.
And the other branch we just don't want to worry about right now.
Absolutely, yes. The optimistic planning definitely is a good way to go. So just what Erica just mentioned, we're going to assume that the dynamics of the world are stochastic. So we have actions that can change the state of the world, but this is not going to be a deterministic process because of things like weather and current. So we're going to maintain a probability distribution over what state might we end up in after we take an action starting from a particular state. And then we're going to have a reward function. And this is going to be the reward we get from taking a particular action in a particular state. So if we go over to Indonesia and we collect nutmeg, that's going to be a high reward. If we get attacked by Somali pirates, that's going to be a low reward. And then we're going to have a discount factor, which is going to tell us how much we care about immediate reward versus reward in the future. And within this instance, we're really interested in creating decision policies, which is a mapping of states to what action or decision we should make. And I'm going to be particularly interested in optimal policies, which is going to be defined by what is the sequence of decisions we could make in order to maximize our expected sum of future rewards. Now, in some cases, we won't actually know what the state of the world is. So this was particularly true for our sailors. They did not have GPS, so they could only get local observations. And in this case, we can augment the MDP framework with two additional variables. One is a set of possible observations, and then the other is the probability of receiving those observations, given you've ended up in a particular state after taking a particular action. Now, in this framework, we can't make decisions based on the state we're in because we don't know the state we're in, but we can maintain a probability distribution over what state could we be in the world. And this has to sum to 1 because we have to be somewhere in the world. And in the discrete setting, that means that we're going to have an S-dimensional continuous valued vector, which is just this probability distribution over where you might be in the world. And we're going to do our policy based on that probability vector. We're going to figure out what to do based on where we think we might be in the world. Now there are a couple different axes in terms of these type of decision scenarios. One is fully observable versus partially observable, which I just discussed. And another is whether or not you know the model parameters for your reward model and your dynamics model. And so in this talk, I'm going to talk about two different types of decision scenarios. One is reinforcement learning, where we're going to assume we know where our ship is, so the state is fully observable, but we don't know what our model parameters are. And then in the second case, I'm going to talk about when our state is partially observable, but we know what the model parameters are in our world. And I'm going to spend most of my time today talking about 3 different contributions of thinking about how we could leverage structure to scale up to some very large problems. And the first thing I'm going to talk about is how we can do fast exploration in large continuous state Markov decision processes with typed noisy offset dynamics. So this is the problem. We would like to figure out a decision policy for acting in order to maximize our expected sum of future rewards, but we don't know what those hidden model parameters are. We don't know the state of the world, or we don't know the dynamics of the world, and we don't know the reward model. Now, one thing you could imagine doing in this scenario is representing a distribution over all the possible model parameters that could be out there, all the different transition dynamics and all the different reward models. And you could compute a policy with respect to that current distribution and the future possible distributions, and try to optimize that exactly. And while that's really appealing, that's piece-based hard to do for general problems. So it's going to be an intractable thing for us to do in the general case. And this is the intuition for that. So there's sort of 2 types of things that we're trying to do if we don't know the model parameters. The first is we're trying to get experience in the world that allows us to estimate them. So you can imagine that if you were a spice trader and you were just starting off, that you might sail all over the world in order to try to figure out where are good spices and what are the best routes to get there. And as you move around in the world, you're going to be getting experience that you can use to estimate those model parameters, to estimate where is there good spices and what are the dynamics in the Indian Ocean and the Atlantic Ocean, so that you can figure out how best to plan. But eventually your boss gets kind of frustrated and says, well, we have to start making money sometime soon. You can't keep going to Antarctica. And so at some point, we're going to want to use the information we have to converge on some model parameters and then decide on what's the best route to go in and where are the best spices. And so most work has focused on approximations to trying to do this trade-off between exploration and exploitation. And in particular, some of the original work focused on asymptotic guarantees, which says that if in the limit of lots and lots and lots of experience and much time, then we're guaranteed to converge to a policy which is identical to the policy we would take if we actually knew what those optimal parameters or those hidden model parameters were.
Emma, quick question. So in your model parameters, do they include the parameters of your reward function as well?
In the general case, they do. In the case that I'm going to talk about shortly, they don't, but in the general case, they do. But this only provides asymptotic guarantees, and that's not very satisfying because that's sort of saying we're going to visit Antarctica 40 times and we're still going to be checking there for nutmeg, in years to come. And so there's been a lot of interest recently on probably approximately correct approaches, which essentially give us a bounded amount of time to do exploration. So these say on all but a finite number of samples, we're going to choose a decision whose value is epsilon close to the value of the optimal decision that we'd take if we actually knew the model parameters. And these were created by people in the late 90s and early 2000s. And the question that these are really trying to answer is how many samples do we need in order to build a good model that we can use to act well in the world? So what do I mean by a good model? Well, we're going to be estimating our model parameters from experience. And in general, the more experience we have, the closer our estimated parameters will be to the true underlying model parameters with high probability. In terms of acting well in the world, if we actually knew what those model parameters were, we could compute an epsilon optimal policy. So we have techniques for solving Markov decision processes to compute a policy if we actually know what those model parameters are. And if we can bound the difference between what our true model parameters are and what our estimated model parameters are, we can then propagate that through to bound the error in computing a decisions policy using our estimated model parameters instead of our optimal true model parameters. And so we can combine these 2 ideas together to talk about something called sample complexity, which is essentially the number of time steps on which we might not act well. This is kind of our budget of exploration, and sort of how much evidence do we need in the world until our estimated model parameters will be close to our true model parameters and we can compute a good policy. And this prior work, this sample complexity that they computed was a polynomial function of the number of states in the environment. Now, the challenge is that in a large number of domains, the state is specified by a multidimensional continuous value. So in the case of, say, a quadruped robot, you have a 15-dimensional state space to specify all the joints. In the case of something like our sailboat or a car, often the state space is specified by the GPS coordinates. But if you have continuous valued state spaces, then you effectively have an infinite number of states, which means that these prior approaches are going to be exploring for a polynomial function of infinity. So they're not going to be able to handle these types of domains very well. And so what we decided to focus on was a particular subclass of continuous state Markov decision processes where the dynamics can be described by tight, noisy offsets. And the idea here is that each state has a known type. And your type plus your action determine what your dynamics model is. So the new state, if you start off in a particular state, your new value after you take an action is just going to be an offset from where you were before, so like a delta, plus some noise, where that noise is a Gaussian function. And the parameters that determine that offset and that noise just depend on the type of the state and the action that you took. So for example, we might imagine that the Atlantic Ocean, because of weather and current, might have a really large noise and a smaller offset on average when we open up our sails, compared to if we're closer to the Indian Ocean, which might have calmer currents and calmer weather. So maybe we have a smaller amount of noise and we get to move further. And even though these sound like they're quite a simple model, they're actually a very expressive model. And they've been used a lot in inference for a wide variety of different types of problems. So people have thought about these for modeling things like human motion. People have used them for honeybee dances. They've also been used for the stock market. So they're quite a simple model, but by using these types of switching systems, you can express a wide class of different phenomena. So this is how our algorithm works. I'll tell you in a second how we compute this policy, but imagine for a second we've computed a policy and we're using it to make a decision and act in the world. So once we act, we're going to update our type action counts. So this is to say how many times we've opened up our sails in the Atlantic Ocean. And then we check whether or not this exceeds a threshold. And if it exceeds a threshold, then we label the type action dynamics as known. And we use that to define an optimistic Markov decision process. So for anything which is known, then we're going to actually estimate the parameters for that known type action from the data we've had in the world. So we can just use our actual experience to estimate the model parameters. But for all the other type actions that we haven't had very much experience in, we essentially just hallucinate that they are incredibly high reward areas. And we set the dynamics for those to be a self-loop. And what this means is that when we actually solve that optimistic Markov decision process, it's going to drive us towards parts of the world where we don't have very much experience. And so we'll solve that optimistic Markov decision process and then use that to decide how we act for our new state. And we repeat this process over and over again. And eventually this is going to say drive us towards, if we start off in the Atlantic Ocean, it's going to drive us towards the Indian Ocean because we're going to hypothesize that there's lots and lots of reward there. And so our policy will drive us that way. Now the important thing is that the sample complexity, that is the amount of experience we need in the world to estimate these model parameters, is only a polynomial function of the state dimension in this case. So a little bit more formally, if we're given a delta and epsilon and a noisy offset dynamics Markov decision process with m types, then on all but a number of steps, which is a polynomial function of the dimension of the state space, the number of types, the number of actions, and several different problem parameters, we're going to be guaranteed to be epsilon close to the optimal value with high probability. So how does this relate to prior work? So originally, when people first started thinking about these kind of bounded amount of exploration models, people did them for very expressive classes of dynamics. So people thought about this where each state could have a different dynamics model. And those were very expressive, but they needed an exponential in the number of state dimensions amount of exploration time. There was also some other models which thought about something closer to switching state models, but they also needed an exponential amount of time to sort of load those parameters. There were some other models that thought about a much more restricted set of dynamics models. So these were linear Gaussian models where you know what the variance is. And these could learn really efficiently, but they were too restricted for a large number of domains. So in order to capture a lot of real-world phenomenon, we wouldn't be able to make this restricted amount of assumptions.
Do you know what kind of assumptions they were making?
Yeah, they were assuming that you know the variance. So they're assuming that you sort of have a linear Gaussian dynamics, but that
I see.
the variance
What kind of domains would that not apply to or apply to? In particular, I'm familiar with the kind of helicopter work of
Right. So, well, one of them was basically a theoretical paper, but one of the instances that we were motivated by was if you think of something like traffic, I feel like the variance on different streets is really important when you do planning. So the offset for a highway is much better than the offset of a small side street, but the variance is really large. So if you're doing something like getting to the airport, you really care about estimating that variance parameter because you might actually go on the side street even though it's slower. So these types of models wouldn't capture that. So you can think of our approach really as being kind of getting closer to the upper right-hand corner here, which is where you'd really like to be. So we are a sort of more expressive class of models than some of these previous approaches, but we still scale polynomially in the, with the number of dimensions in terms of the amount of experience we need in the world. And you can see this on this simulation example. So this was a simulation example that came up in the mid-90s. And this is just to demonstrate that there were previous existing examples which fit our assumptions of the type of models that we could handle. And you can see that compared to some other approaches, we learn really quickly because essentially the dynamics here is the same throughout the environment, and we can learn those parameters really quickly and then start to do very well in terms of our performance compared to some other approaches which are essentially trying to model very different dynamics all over the state space, and so they take much longer to try to find a good policy.
I'm sorry, I may be looking at the wrong time, but so on this opportunistic, the optimistic aspects of things, stop that video. I don't want to miss it. When does that get you in trouble, though? I mean, making that assumption to explore these spaces that you think will be, saying that they're
going to be fabulous. Well, it's bad. So I guess one assumption I probably made, you have to assume there are bounded rewards. So if it's possible that like you could, if the world was flat, for example, this would have been a really bad assumption because some of you would have basically jumped off the cliff at least once, in fact, multiple times to make sure that you really do die every time you jump off a cliff. So you have to assume that the world is bounded and there aren't catastrophic failures. So in terms of things that you could do.
What about the cost? Does the costs of those wandering into costly space that don't kill you but are very costly?
So that you assume that you will get hit by those, but that then you'll get to act really well on pretty much everything else. So over the long term, you're going to still be getting good performance.
Okay.
So, I mean, one thing I'm confused about this, so you're assuming infinitely dimensional state space. Is that correct?
Well, it's not infinite dimensional, finite dimensional.
Like,
yeah,
so
infinite number of states.
Infinite, cardinality is infinite, right? So that means, no matter how much exploration I do, there'll always be, some place in the world where I'll have, good reward, right? And why don't I just keep exploring? I mean, what makes me...
Why don't you keep exploring? Well, I'm assuming there's only a finite number of types and actions, and that's what's determining the dynamics models.
Yeah. So in a sense, you're kind of considering a cluster of states. I mean, yes. And each cluster is infinite dimensional. I see.
Yes. So I'm only learning the parameters at that more aggregate level, and that's what's saving me.
Do you know initially when you will learn something? How do you know that you learned something?
It's when you hit that threshold. So
you initially know the threshold.
Yes. So you can compute the threshold for a particular domain based on the number of types and actions. And that gives you how much experience you need for each of the type actions. And after you've hit that threshold, you label it as known, and you don't do any more exploration.
So is it a static threshold, like visiting the state 3 times? Or can I define a dynamic threshold, like if the variance among the times I travel this drops below this threshold? Can I do a dynamic threshold?
So for the bounds, it's a fixed threshold. So the bounds give you a number. They'll say, people use 5 or 10, the bounds are actually more like 1 million. They're very, very loose bounds. So, I mean, they're tighter than if you assume an infinite dimensional or infinite state space, but they're still loose. There have been people who are thinking about the variance of the dynamics recently in terms of similar bounds, but it's still a hard threshold. It's still, 17 or things like that.
Are those bounds, was the computation of those bounds somewhere in a previous slide, or that's off?
I have not shown you the proof for how we do that.
But was the equation there, or?
Yes, this is the equation.
So the bounds are where?
So this is the number of steps you need, and essentially the number of steps you need per type action is if you remove this. So you basically need a polynomial function of the number of state dimensions and all of these parameters, and that is the amount of experience you need until a state type action becomes known.
And that will make you epsilon close
to the optimal policy with high probability.
So it's kind of a Chebyshev's kind of a proof.
Yes. Yeah.
So now that you've clarified a bunch of things, something that I don't understand anymore that I thought I did. So I understand that you've broken things up into classes, and now you have a finite number per class that you can say, okay, now I've learned it, and you have a confident model about that particular aspect. So the question I have though is that if the classes are not pre-known, like, because you're inferring these classes as you go along too, right?
No, so these are known.
Oh,
yeah. So
are.
it's like you know you're in the Atlantic Ocean, or you know in your.
I see. So you have a fixed set of classes, and the classes are known when you start.
Yes, and they're fully observable.
Okay.
So, yes.
Got it.
Yeah. No,
So I can imagine.
Thanks for asking.
So I can imagine that kind of thing being a nice refinement that wouldn't necessarily explode, having the probability distribution over class types and other, for example, the famous n and other, and updating that as kind of more of a standard Bayesian update problem on top of all this that would create another loop.
Right.
Yeah.
Probably be harder to get bounds in that case.
Yes, because the other would be quite scary.
Yeah. So is this hard switch from like unknown to known kind of required for those bounds, or like, I mean, could you compute bounds in the same kind of setup where you do this switching model, but where your exploration-exploitation trade-off is kind of more continuous and can keep going throughout time? Or is it...
Or do you have to have the... No,
right.
it's a great... You can do it in a very similar way when you do have this more fluid approach. Okay. So some other people have thought about this, not for switching state models, but there's these sort of interval estimation approaches where essentially you just have a bonus that depends on how much experience you've had so far, and those smoothly trade off. Even those, often they'll at some point say, I've had enough experience and stop updating it, but they can be entirely smooth. And you can prove similar pack-style approaches. Yeah.
But also, like, your parameters are just mean and a variance of a Gaussian, right?
Yeah, for each of the type actions.
So you can simply do a Gaussian inference where, you basically fit a string, like complete Bayesian inference for a Gaussian model, and that will allow you to do a smooth transition.
Yes, you could do that as well. And then you just want to... basically, you have to propagate that information into how much uncertainty could you have over your value function in terms of the bounds. And so how far away could you be from the optimal solution? Okay.
I hope you don't mind these kind of...
Oh, no, it's great. So the other question then is sort of, these models are fairly simple, and so it's good to make sure that they are realistic to capture some of the domains that we would like to. So actually I'll explain the robot navigation first because it's moving. So we were interested in this. I mean, this is obviously a small example, but you can imagine the Mars rover has to go over different types of terrain. And so in this case, we have a Lego robot. The pattern on top of it allows the camera to recognize where it is in the environment. And it's trying to learn how to navigate over rocks and carpet in order to reach destinations. And so it's learning that there's a different type of dynamics over rocks than there is in carpet. And in particular, it's a little hard to see, I guess, but we have this outline, and outside of that is out of bounds, and it gets a high penalty if it falls out of bounds. So it does kind of a conservative turn on the rocks because it's more likely to get tripped up by the rocks and maybe go out of bounds. And then it can do a tighter turn over here by the carpet because its dynamics are, have a smaller amount of noise. And then the other case we looked at, and we did this in simulation, but we sampled from real data. We thought that this could be really relevant for things like roads because there is very different variance and different offsets. And so we thought about interstate, local highway, and small side street roads. And MIT has this project called Cartel, where they collected a bunch of data with real cars over different types of roads. And so we did this in simulation for a small sort of grid world environment, but for the different types, we'd sample from these actual data sets of highways and small side streets. And we found that even though the switchy model was a pretty coarse approximation, it was still able to get very good performance, and having multiple different types was beneficial. And I'm happy to talk more about that at the end if you would like.
While we're on that topic, so the idea is you have variances by time of, means and variances by time of day?
No, just by type of road.
Just by type?
Yeah, but you could have it, I mean, time of day could be a type as well, but in this case it's by interstate, local highway, and small side street.
And are you sampling to learn in real time? Or you come up with plans for over averages?
You're doing it in real time. So like you've just moved to your new city and you're trying to figure out the best way to go to work. And so each day you're trying out different things and how much experience do you need in terms of figuring out what's the right way to drive to work, in terms of the variance and the mean offset that you want to have.
You definitely have lots of data around here about variances of roads and side streets and so on.
I would imagine it should be really a lot of fun. So really the key contribution here though was the theoretical aspect, showing that we could do provably efficient exploration in this expressive class of continuous state Markov decision processes. I'm next going to fairly briefly talk about how we did efficient planning in a large linear Gaussian partially observable Markov decision process using macro actions. So just to recall, in the partially observable Markov decision process framework, we're now assuming that we know what the model parameters are for our dynamics and our reward functions, but our state is hidden. So we're going to be computing a policy for distribution over where we think we might be in the world. And the challenge in this scenario is that, again, if we're interested in sort of continuous valued states, then we would have a probability distribution over an infinite dimensional space. Because we'd have sort of an infinite number of states we could be in, and we want a probability distribution over that. And so aside from some restricted cases, the generally existing methods don't scale to this type of problem. And so just briefly, we assume that you have sort of linear Gaussian dynamics, which is very common in particularly robotics domains, and an exponential family observation model. And essentially, if we restrict our world to this, we can compute very efficiently what beliefs might we end up in after a sequence of actions, regardless of the observations we might receive during that sequence of actions. And that allowed us to evaluate conditional sequences of short open loop policies, which we call macro actions. And this allowed us to scale up to much larger long horizon POM-DPs. I'm not sure if this is going to be at all visible when I go to... All right, let's see. I wonder, is there any way to turn down some of the lights?
Yeah.
Ooh, I was going to say, ask and it will occur. This is fabulous. All right, let's see if I can make this go. Oops, that didn't work. Gonna go? Let's see if I can press. Okay, good. All right, so we did this for a helicopter. So we had an autonomous helicopter, which you can see flying around a little bit up here. And it was a monitoring and surveillance task. So the idea was that you wanted to know whether or not these suspicious vehicles were going inside highly sensitive areas. And the helicopter has a camera underneath it. So you can see that if it flies higher up, it can see more of the environment, but at a lower level of resolution. And then when it flies lower down, it can see less of the environment, but it gets more accurate observations. And its goal was to sort of fly around and correctly report whenever any of these targets go into this area. Okay.
And flying up and down is basically just to trade off the resolution of what it could see at any moment.
Yes,
versus
exactly.
being able to be shot down if it's lower.
Right, we did not include that. Yes, you could add that in as well. The visibility of the helicopter.
Catastrophic failure.
Yes, we did not model this as accurately as one might imagine.
That could have been interesting though too.
It would be. It'd be cool because you'd want to be like lower and you'd be
Get down and get back up again quickly. You know?
Exactly. And in this case, and what you can see here is the colors is just that we have a laser range scanner on top of the helicopter. So the helicopter actually doesn't know exactly where it is, so it's localizing itself through the laser range. But the important thing about this environment is that it's really large. So depending on the number of targets you have, it's somewhere between 12 to 24 dimensions, because each of the agents on the ground have an X, Y, and orientation, plus the helicopter zone X, Y, Z, and orientation. So it's a really large problem, and a lot of the sort of standard discrete state POM-BP planners just can't scale up to this size of domain. It's very, very large. But they say, and the lights can go up again if there is. That would be pretty crazy. Wow, awesome. But the exciting thing is, too, is that even for this type of domain, you can always come up with some heuristic approach to solve really large problems. And the cool thing about this was not only could the sort of principled approaches not scale up that were reasoning with discrete states, but the heuristic approaches just didn't do as well. So we videotaped this to get ground truth, and we compared the number of times the algorithms correctly reported when targets went in versus the number of true target entries. And our approach did much better than the other approaches in terms of correctly reporting when targets entered. This approach, nominal belief optimization, has been really popular actually over the last year. There's been a bunch of papers all thinking about this idea. And essentially it's just to assume that the observation you get is the one you expect to get. And that really reduces planning, because you don't have to think about all the observations you'd get. You just have to think about the observation, the mean observation. So it's much more efficient, but it doesn't do as well in a lot of environments where you really need to think about the conditional nature of under different observations you'd really want to do different things. So for example, in this environment, you might have a really large variance. And if the agent stopped, then you might need to wait and see whether or not that target actually continues going towards the sensitive area or not. Whereas if they have already passed the sensitive area, maybe you don't need to worry about that anymore. So you really want to think about, under different observations, what would you do compared to assuming the mean. Okay, so now I'm going to talk about efficient planning in large discrete state POM-BPs with prerequisite structure. So I've mostly talked about so far examples where we can characterize the state space by a number of different continuous valued variables. But there's obviously also a lot of other applications where that's not a very good model. So for example, I think right now there's a lot of interest, particularly after Watson, on speech recognition and speech assistance systems. And you could imagine for something like travel reservations, you want to identify where someone's going from and where they're going to and the date. And while there are a lot of airports in the world, there's still a finite number of airports. And it doesn't make sense to model things like the from and the to airport as a continuous valued variable. Similarly, something like network structure, you might have a bunch of different nodes and they'd either be up or down. Again, that's not a continuous value. And then finally, education, which is an area I'm really excited about. So if we think about how you would do automated tutoring for arithmetic, we'd like to be able to compute a policy to select actions, which are sort of these pedagogical activities, to help a student master a bunch of skills. And we can frame this as a partially observable Markov decision process. So the set of states we have is perhaps a number of different skills and whether the student knows or doesn't know each of those skills. And then the actions we have access to are essentially going to be along the continuum between testing actions and teaching actions. And then we'll get observations back from the students, which are things like whether or not they answered a question correctly, if they're asleep in class, or a number of other types of responses that the student could give us back. And then we have two different, we have the transition model and we have the observation model. For the transition model, it encaptures how different activities help a student probabilistically transition between a previous knowledge state and a new knowledge state. So how much does a calculus test help a student know calculus versus an observation model which says what's the probability of a student responding with a particular observation after experience and action and transitioning to a new state. So this might be like something, if a student has a calculus test and knows calculus, what's the probability that they'll do well on that test? And so using these models, we can represent a belief state over the student state. So if we had a sequence of different activities and answers from the student, we could represent a distribution over the states we think the student might end up in. So for example, it might be most likely, given that sequence and assuming our model parameters, that the student has mastered 1 by 2 digit multiplication and 1 digit division, but still doesn't understand 2 digit long division. And using this, we want to compute a policy to optimize learning. So for example, a policy might look something like this. You might start with some instruction, and the student would listen, which doesn't give you very much information about whether or not they know it, understood it. And then you would give them a drill exercise. And based on whether they got that right or wrong, then you could give them another activity, such as a drill exercise. And if they got the second one right, maybe they're now ready for some harder material. If they got the second one wrong, maybe they were just lucky and guessed correctly on the first one, and we actually need to back off and check that they actually really understood that earlier skill. Now, there's been a lot of work on intelligent tutoring systems. I think really people have been interested in education and AI pretty much as long as AI has been around. But I'm going to focus particularly on other approaches that are to do with sort of this notion of how do you do planning and sequential decision making. Some of you might have taken the adaptive GRE. That's basically trying to give you different types of questions, but according to what they think you know and don't know, but only for assessment. So it's not actually trying to help you learn anything. There's been quite a lot of interest, though, in people doing sort of a Bayesian modeling of student state, kind of keeping these belief states over what people know or don't know. But there's been very little on trying to think about how would we do teaching policies as sequential decision making under uncertainty. There's been some work where they've thought about the state being fully observed, but I think that it's really much more flexible and better and robust to think about the state being hidden and getting sort of noisy observations of the state from the student. There's also been work where people think of the state being hidden, but using a greedy, so not sequential decisions. And the reason I think that is important is because of the following example. If you think of only getting a single hour to teach someone calculus, you wouldn't give them a test, because if you want them to learn as much calculus as possible, you'd maybe give them a lecture or give them an exercise or something like that. But you wouldn't get any benefit from the diagnosis. So there'd be no reason if you only get a single interaction with a student to do diagnosis. But if you know you get to interact with a student for an entire semester, doing a diagnostic test could be really helpful, because then you'd know what they understand or don't understand, and you could focus on that for the rest of the semester. So if you do greedy approaches, information gathering or diagnosis just is never going to be worthwhile. But if you can think about it on a very longer term sequence, then you can start to interleave these type of things. Okay, so let's think again about arithmetic in particular. I would argue there's a lot of different skills that are included even in very simple arithmetic. So something like a fourth grader you'd like to learn. So they might have things like 1 by 2-digit multiplication, subtract fractions with different denominators. You could write down a lot of different skills. And I'm going to pick 122 skills because you can easily come up with this many, and it's an example we have later. But if we have 122 skills, then that's a 2 to the 122 state space, which is approximately 10 to the 30. And that is a massive state space for any sort of existing partially observable planner. We can't scale up to anything like that. We can maybe scale up to 10 to the 5, definitely 10 to the 4, probably 10 to the 5. But I would argue there's sort of two concerning things. One is that this is only a small problem. I'd love to be able to do this for K through 12, and this is only fourth grade math. And secondly, we don't even know which state the student's in. So which of those 10 to the 30 states is the student in?
Also, there's this interesting assumption that these are independent, and I know there are probability distributions going between these states, but sometimes you learn something a little bit more deeper, and you actually get everything else for free.
Absolutely.
Opposed to them being all separate states.
Yes, and I don't talk about that in just a minute.
Yeah.
So the first idea is that to tackle this, we're only going to consider the probability of the student being in a subset of states. So imagine this is your belief state, and this is the probability over all the states you're in, and I've put up 16 there, but you could imagine, a billion. It just would go off the page. So instead of thinking of the student being in all of those states, we could kind of think about the student being in a subset of states or a massive aggregate out state, which basically captures all the other states that the student might be in. And this is really a novel extension of the notion of envelope planners, which came up in the Markov decision process community in the mid-90s. And what they were interested in there is that even if you know what the state space is, if your state space is really, really large, it may be intractable to plan over all of it. And so maybe you could just consider a subset of states. And what I'm proposing here is that we could do something similar in the partially observable case, where we just think of the probability of being in a subset of states instead of all possible states. And what this really is a mapping approach. We're mapping our state space into a much smaller state space in the hopes that if we get it to a small enough scenario, then we could use existing approaches to solve that smaller state space. Of course, kind of the key question is, well, how do you pick the smaller state space? And this has to do with something that Eric was just alluding to. So we can leverage the dynamics of these type of problems in order to efficiently compute a good subset. And in particular, these things called learning hierarchies. So these were first developed by the education community in the 70s and 80s because people were really interested in what is the prerequisite structure among skills for teachers to know when they're teaching things. And this essentially expresses what skills do you need to have before you can master other skills. So for example, I don't know anybody that understands calculus that doesn't understand addition. And so you don't really need to worry about the student that has mastered calculus but not addition, because that's a subset. So just to be kind of precise about the type of problem DPs that I'm creating the solution for, we're focusing in on things with positive only effects, which means that once we make one of those skills true, we assume they stay true. It's essentially like no forgetting, which I certainly don't fit, but this is a common approximation in the intelligent tutoring systems community, so it was a reasonable place to start. And then the other, probably most key assumption really is that we assume that if all your preconditions are satisfied for a skill, that the cost of making that skill true is independent of the values of all your other variables. So this is like saying if you've got all your preconditions for calculus, then it doesn't matter whether you know medieval history or abstract algebra, that the cost of helping that student master calculus is the same, regardless of those other skills.
So you can come up with some obvious examples where that fails?
Yeah, I think there are cases where they may not be strict preconditions, but two things might help you learn something else faster. I've definitely had that experience in my own life. Like if you're sort of learning about, say, computer architecture and assembly language, sometimes like thinking of things from the bottom up and the top down can help you learn things faster, even though they're sort of independent. So to create this initial envelope, you can sample initial state from that possible initial belief state. And then you just create a trajectory from that start state to the goal state. So our goal state is going to be where all of the skills are true, and our start state is going to be where some of those skills are not true yet. And we can just compute any trajectory that goes from the start to the goal that satisfies the prerequisite assumptions. And this is just computing a topological order, so it can be done really cheaply. Just linear in the number of variables and the number of precondition edges.
Just to make sure. So you're taking the structure that Gagne had?
Yes, that's input, yes. And there's definitely really interesting questions about how do you get that structure. So what this does is that this means that the number of states we end up with is linear in the number of state variables. Because when I create that trajectory, I'm essentially just flipping each bit to be true. So at most there can be n flips if there are n bits. So this is taking us from a 2 to the 100 state space to 100 states, which is good. We can hope to plan with 100 states. So our algorithm is called a reachable anytime planner for partially sensed domains. And the idea is that we use the method I just talked about to create a subset of states we're going to plan for. And then we create a new POM-DP where we put all the other states into an aggregate out state. And we redirect any transitions to that out state if they would have taken us outside of the envelope. We make this out state a sync state, and we give it a large negative reward. And that basically just penalizes us from falling outside of the envelope. And then we can do planning. So this is, 100 or a couple hundred size state space POM-DP, and there are existing planners that can be used to solve this. And then if we have additional time, we're going to expand the envelope to include more states, and then repeat this process and go back to 2. So it's an anytime planner.
Just for clarification, are you assuming that when I ask you a question for evaluation, you give me an answer? After that, I certainly know what you know.
No, I'm not assuming that it's an oracle. No. So I'm assuming there's noise, and you could guess correctly even if you didn't know, or you could make a mistake even if you did know. So the first thing is sort of a sanity check. The hope would be if you have tons and tons of computational time, eventually you could guarantee your approach would relax to an optimal approach or an epsilon optimal approach. And eventually, if you keep doing this expansion process, your envelope will eventually include all the reachable states. So at that point, as long as you're using a planner that has some optimality guarantees, you're guaranteed to converge to an epsilon optimal approach. This is sort of a good sanity check. But in practice, most of these problems are going to be way too large to include all of the possible states. So it's important to have performance bounds in the meantime. So there, we provide upper and lower performance bounds. For upper performance bounds, it turns out that if you think about the fully observed problem, it turns out to be really cheap to compute the cost of making computing the cost of making a number of different skills true if you're in the fully observable case. It's essentially a stochastic shortest path problem. And because you have this independence relationship that as long as all of your prerequisites are true, the cost of making this new skill true is independent of everything else. It means that you have a lot of path independence in terms of the values. So it turns out that we can compute the fully observable MDP values in time that's linear in the number of state variables. And then to get an upper bound on our POMDP, we just take a weighted expectation over our belief that we're in each of those different possible states times the MDP value. Now for lower performance bounds, we essentially just put a large negative reward on that sync out state, and that means when we compute our POMDP values, then they're guaranteed to be a lower bound on the true optimal values. Because we're essentially saying every time you fall out of your envelope, it's really bad and you'll never escape, and it's really a negative reward there. Mm-hmm.
Maybe there's something that I missed earlier. So then are the states that are in your box going to start with like only the achievable states based on that hierarchy of states? Is that where they're coming from?
Yeah.
I see. And how much does that reduce the overall, like you start out with 10 to the 30th, you're saying, how far does that bring it down?
Right, so well, I guess so there's two parts. There's the reachable state space is smaller than 10 to the 30 just because of the precondition structure. And then inside of our envelope there is a subset of that.
Oh, I see.
Yeah,
How
so
do you choose the subset?
we choose the subset by just picking any precondition. We basically start from a possible start state to our goal state, and we pick any sequence of states that satisfies the precondition structure. So just some possible trajectory. Some path. And then as we have more time, we add in more possible paths.
I see.
To that
So if the person somehow, well, that's interesting because I mean it seems like the person might be able to step off the path and then end up in the out state.
Absolutely. Yes, and so that's the problem is that like you could, depending on how many trajectories you've added so far. So normally it turns out if you, I'll show you in a second in terms of the results, but normally only one trajectory isn't sufficient. But if you have several, then you can start to do pretty well.
How would you expand it? Like, is there
There's a lot of different ways. We do it pretty simply. We just add in, first we prioritize adding paths from other possible initial start states to the goal. Then you could also think about when do you hit fringe states on your policy, things like that. But I think there's a lot of interesting ways to go. All right, so this gives us a lower performance bound. And then we did 2 simulations of tutoring problems because I'm particularly excited about those. And the goal in this is to make all of the skill variables true, and you get a big reward when that occurs. And our baselines are a couple of generic POMDP approaches that are sort of state-of-the-art but handle any types of domains, and a heuristic that's used actually in a commercial tutoring system. So this heuristic essentially identifies all of the goal variables whose probability of being true is below a threshold. So I want you to learn calculus, but I'm only 50% sure you've learned calculus and I need it to be 95%. And then they just select any of those things that are below the threshold, or they select the one with the lowest probability and then pick the best action to make that true. So they assume that all skills are independent and then just focus on getting all of them to a higher level.
And have these systems been evaluated formally?
Yeah, I mean, I think they're used with roughly 500,000 people. You mean like decision theoretic formulae, or in terms of like, do they actually help students learn?
The latter.
Yes, they do help students learn.
But has it been characterized? In other words, if you're going to pose something different than this heuristic, you're asked to do a neck-and-neck evaluation study. Say, well, how much better is it to do X versus Y versus human, for example?
Oh, how much better is this than human, or
how much better is a less heuristic approach than this?
Right. So I don't know. I know that they've been used in schools, and they do pretty well. I mean, I think they often get like 1 standard deviation better than not using them, but I'm not sure if they compare it to human tutors or not for this.
And how about your methodology you can propose?
I haven't done. So all the stuff I'm talking about right now is simulated students. So these are so far the results are just for simulation, whereas these have also been extensively evaluated in real students. These are commercial systems.
But they actually use the probability in a widely used way.
Mm-hmm. Yeah.
And typically, what is the the base source of the probabilistic inference in most of these systems? Is
In
it-
these other systems, how are they, or how are they doing the
Yeah,
inference?
you know.
I mean, they assume all skills are independent, so it's pretty easy to do the updating. So all the skills are independent, and then they're just sort of modeling. They basically have a sort of a slip parameter and a guess parameter. Sort of what's the probability of someone accidentally messing up, even if they know something? What's the probability of them guessing, even if they don't? And what's the probability of them learning it with each activity? But they model all the skills independently, which makes it much simpler.
Is your impression they learn those from data, or they're hand-assessed by experts?
Some of both. Yeah. Now they have a lot of data, so they can learn those better.
Out of curiosity, how long have these systems been used with probabilistic updating?
I think the knowledge tracing stuff that sort of this independent updating came out in the mid-90s or maybe early 90s. John Anderson from CMU, I think, was, and Albert Corbett.
So I'm surprised that John Anderson would be using probabilities in the system.
Pretty sure it was Albert's. Pretty sure it was John Anderson and Corbett. First for computer programming systems, now for math. So the first thing we looked at was a very creatively named small math domain because it's small. And there are 19 different skills. And you can see here the precondition relationship among these skills. So there's a lot of precondition structure. And we had different types of actions. We had actions that were drill exercises, which would give us more information about whether or not our simulated student had mastered that skill. And then tutorial actions that were supposed to be sort of something like instruction. And if we compare it to sort of these standard algorithms, sort of the state-of-the-art but generic algorithms, they just fail to scale up to the size of domain. It's a very large domain, and they just can't handle it. But what you can see here, and this is a little bit related to one of the questions I was asked, that after a small number of envelope expansions, so if you only do one envelope expansion, you're not doing very well. But if you add in some more states, then after a small number of envelope expansions, you start to get pretty good performance. And you can see there an upper bound on the type of performance we could achieve. And if we quantify this in a little bit different of a way, we can think about what's the average number of steps until our simulated student can get to the goal, so they can master all of the skills. And in our approach, it took them on average 34.5 steps with an average over 200 trials. Whereas if we looked at the commercial tutor heuristic policy, it took almost double that number of steps to get to the goal. And that was even if we picked the best threshold. So you could think, do we want them to be 95% sure they've mastered the skill or 80% sure they've mastered the skill? When do you consider them to be done? And this was statistically significant. And this was encouraging because I think it really highlights the potential benefit of thinking about this as a sort of formal sequential decision process as opposed to just heuristic approaches. The second one we looked at was more arithmetic simulation over a number of different types of problems, and we combined together learning hierarchies from the literature. So that's what this network represents. It's 122 variables of these combined learning hierarchies. And this is just much too large to try with standard state-of-the-art POP-DP approaches. So really the only one we could compare to was this heuristic policy, and there were two instances that we tried. So we used the standard algorithm, which would ignore any structure among the precondition skills. And if we did that, then it just failed. It can't handle this type of domain. It's really large, and it'll sort of be working on skills that look low probability, but it won't have done its prerequisite skills yet, so it just fails. If you include the prerequisite structure, which is stuff the standard algorithm doesn't have, it still performed worse than our approach over a very large number of thresholds we tried, and performed comparable at one threshold. So I think that this sort of really highlights the benefit of this style of approach over the prior approaches.
So when you say you include the prerequisite structure, is the baseline then basically saying that, okay, I know what the hierarchy is, and I'm going to work on skills that are precedents until they're mastered, and then I'll move to the next one. Okay, yeah, that's
exactly.
a very reasonable baseline.
But really, we'd like to try and see whether or not this actually impacts learning, not just simulated students. It's a little hard to see this one, but I'm also really interested in how we can use information communication technologies for international development. And there's been interest in how do we do sort of intelligent tutoring systems in the classroom for places which only have a few computers and not enough for one per child. So in a lot of these scenarios, we've had scenarios, people being interested, well, this comes from Microsoft, where we have multiple different input devices for the students to use at once. As a way to allow multiple students to interact and have good experiences with the same computer. But within these settings, there can be a challenge in that if people have different abilities or different backgrounds or different interests, it can be hard to keep all of the students engaged and challenged at once. And in particular, if you're sort of in competitive scenarios, one person may dominate the interactions, which may mean that it's really hard for the other students to keep engaged and may end up having negative learning repercussions. So our idea was, well, what if we tried to do some amount of personalization? So we'd like to make it so that all students are kind of working at their own level, and by doing that, we should sort of be able to equalize the playing field. So we made this simple group math game where we split up the screen into different segments. So each student is working on their own segment, but they're competing to be the first to answer 12 questions correctly. So they're each doing their own drill exercises. And then the idea is that we're going to personalize what questions they actually get using our Markov, our partially observable Markov decision process. So we're going to keep our belief state estimate over what they know or don't know, and then ask them questions accordingly. So maybe Eric's working on calculus and I'm working on addition, but we still have the same chance to win. And we did this user study with 2 elementary schools in low-income areas of Bangalore, and we did it with 4th and 5th grade students, and they had 4 sessions with the software tutor. And encouragingly, we found that game dominance was reduced. So we tried to quantify game dominance in 2 different ways. One is that a single student was winning 80% or more of the games, and another was where a single student won 10 or more times than any other student in the group. And in both of these settings, our adaptive condition, where we're using the POMDPs, had many less instances of dominance compared to if we were randomly selecting questions for each student. So this is hopefully going to increase engagements amongst all the students. But again, you know, we care about engagement, but really the long-term objective is learning. And so while we've got some encouraging results on a concept learning task that I was doing with some computational psychologists at Berkeley, I'm also collaborating with the Pittsburgh Science of Learning Center and Carnegie Learning on doing classroom studies with algebra 9th graders to try to see whether or not these decision theoretic approaches actually lead to better learning.
Yes, I think evaluations would be so critical in this. When the hard stuff hits the really soft stuff, it's really nice to figure out whether or not some of the deeper reasoning methods have an influence of some kind, and how much, if any.
Right. Yeah, because you can always have heuristic methods to solve these problems. The question is, are we getting an advantage by doing this extra machinery?
Or it might turn out that you want the machine learning, but they're very sensitive to the formulation, and they're so sensitive that the heuristic methods that are better at capturing expertise and human expertise might be better, but by the fluke of the expertise, not by the machinery that's used to inference. So
right, yes.
This is the kind of thing that bothers me all the time. I live in this trade-off space, so I think evaluation would be really, really critical there.
Yeah, definitely. And one thing that we were actually just talking about this morning is just that in general, these parameters probably will be impossible to know exactly, and so how can you be robust to sort of uncertainty in the parameters? But the contribution here really was showing that this prerequisite structure really enabled us to do this exponential reduction in the size of the POMDP.
Sorry, again, just go off on this. So I think, for example, it's my intuition is that this is very much focused on the steps and the conceptual space of learning for a human. And in reality, it might turn out, for example, that engagement and attention management is so much more important than the subtleties of the sequence. And if anything, the sequence reveals something about where it's based more in notions of attention, and just comprehension is the probability of the difficulty comprehension leads to a lack of attention. So it might turn out that the whole revolution in education will come on from a sequence of attention management, how you manage attention and engagement over time, and not necessarily secondarily so the actual content.
Definitely.
That's just an example of of a kind of horn that might blow from the east really loudly. It's the engagement and attention that's really critical here.
Yeah, no, I definitely think so. And I'm really excited to talk to Desi Tan later, because I feel like being able to model that and monitor that in terms of maybe brain-computer interfaces and stuff like that, for motivation, I think it is really important. Motivation and frustration are very critical. But just to go back to here, so this technique really allows us, it's definitely relevant to tutoring, and that's why I was first excited about it, but it also applies to other generic forms of POMDPs, and this notion of just restricting yourself to planning over a restricted state space and doing belief state planning over that is more general even than the envelope planner that I proposed here. And that this can really enable us to plan in domains that are much, much larger than was previously possible. Okay. So I've just talked to you so far about 3 different projects that I've done in decision making under uncertainty, and that's really the bulk of the way that I spend my research time. But I've also been fortunate to spend some time on a few other projects that I just wanted to briefly mention. So I come from a robotics lab during my graduate school days, and a lot of interest there was how do we build sort of maps of our environment, and how do we build maps of our environment that might be particularly suitable for humans to interact with computers that are using them, computers or robots. So things like topological representations of environments or hierarchical representations of environments. We are also interested in things like how could you enable better sort of robot human-computer interaction in terms of inferring when someone said in natural language speech a set of directions, what underlying physical path are they referring to? And I'm also interested, as I said, in international development and technology, and I've worked on a number of projects related to that, including things like what's the best way to have low technology literacy users use cell phones in order to enter in, say, healthcare data. We were doing this for a tuberculosis application where we wanted healthcare workers to be collecting data regularly. Was it better to do something like mobile phone or use the mobile phone for voice or for text message or other interfaces? I've also been interested in how do you optimize health worker visits. A lot of health workers travel really far distances. This is Rwanda, where the travel time is definitely significant, and you could use, say, the traveling salesman approach to try to optimize. And I've also been interested in things like health modeling. So how do you know what the prevalence is of a disease across the world based on a meta-analysis of studies?
By the way, on that map, is that really hearing losses, right?
Is that really yeah, so this is hearing loss, and these are, I mean, this unfortunately can't show you the uncertainty over these estimates, but yeah, the highest hearing loss generally is more over that area.
Why would that be?
Why would it be higher in Africa?
Yeah.
Well, the studies have shown that it's generally pretty high. I mean, you can sometimes see some...
in industrialized cities, you have a problem with hearing loss. But...
Well, you can see some interesting up and down. So sometimes it is bell curve where, like, in really rural areas, it'll be lower, and then, like, it's higher in, say, industrial, and then it's lower again as you get to higher income. There's also war, so that also has an impact.
Disease basis for pathology there, but it's just pretty striking, that picture.
Yeah, well, this is a little over. This is this isn't the final one that we ended up doing, but you can see a map of just how it changes over the world, and this isn't the final example. So just going forward, I'm still really excited about decision making under uncertainty. I think it's a really fascinating area, and I'm particularly excited about sort of continuing to tackle some fundamental questions inspired by real applications. So one of the things I'm really excited about is thinking about how can we use population data to do better new personal policies. So the example for this that I like to think about is if you have a new patient who comes in that was just diagnosed with colon cancer, how do you leverage all the prior data you have about other colon cancer patients and the sequences of treatment decisions we did for them and those outcomes in order to construct a better treatment plan for the new individual? And the reason this is hard in terms of a decision theoretic approach is that you're basically doing off-policy learning and off-model learning because the prior patients were slightly different and you didn't explore all of the prior policy space inside of that prior set of people. So I think that's a really interesting question, and I think there's a lot of potential impact on things like health and marketing and stuff like that. Second, I mostly talked about today how a single agent could make decisions in order to optimize some objective. But I think it's also really interesting to think about how we could modify another agent's decision making through the use of incentives. And I think of this as really being kind of the intersection between inverse reinforcement learning and mechanism design. So how could I observe another agent's decisions and then from that figure out enough about their preferences in order to provide them with alternative incentives to get them to follow a policy that I'd like them to follow instead. And I think this would be certainly relevant to things like modifying people's health behavior, things like exercise, things like nutrition. I'm talking to someone from Berkeley who works on an email system to help people change their nutrition and exercise, which is currently rule-based, but I'm talking to her a little bit about whether we could do something like this. And I also think there's some really interesting, challenging questions here. So in general, preference elicitation is also a piece-based hard problem. It's a very hard problem. But we don't really need to know exactly what people's preferences are in order to change them. So it might be that as long as I know you like a Big Mac roughly this much and you like a salad roughly this much, that I could figure out incentives to change the ordinal relationship amongst those in order to change your policy. Because I think one of the exciting things we do get in terms of making decisions is that we ultimately, at least in the discrete action space, just care about ordinal relationships amongst actions instead of actually their value. And then finally, I'm still really excited about the education space and particularly group tutoring. In the case I just showed you earlier, we treated each student individually, but I think once you start to think about the students together, there's some really exciting things. One is you get this combinatorial action space. So if I recognize that Johnny doesn't understand fractions and Susan does, one of the things I can do is I can have students then help Johnny with fractions. I also think there's some really challenging things there with content creation. I haven't thought in detail about this, but I could imagine doing something like inverse theorem proving to try to automatically generate content. And I also think there's some really exciting challenges in terms of visualization and decision support for teachers. So I love this picture because it's from a colleague in Chile. And he does these great things where he projects on the wall sort of these massive grids where each student is working on questions on a different grid cell. And then the teacher can monitor all of them and go in and change which exercise each student is doing. But this is a massive space. I can't imagine looking at 40 different belief states for a student and trying to figure out, like, well, what does that mean about what I should teach tomorrow? And so I think there's really cool decision support questions there where you could say things like, look, 40% of your students don't understand fractions. Or instead of having everyone go to the same recitation every week, you'd make it dynamic. So each week you'd say, all right, you get assigned to recitation 2 because everybody else in recitation 2 doesn't understand long division. And so you could reduce the variance over which teachers are trying to teach. So I think there's some really exciting questions there as well. So just to summarize, I think that sequential decision making under uncertainty is really a key part of artificial intelligence and machine learning. I presented several algorithms for subclasses of problems where we achieved orders of magnitude improvement compared to prior approaches. And I'm really excited to continue to work on some fundamental challenges inspired by real-world applications. Thanks.
Any questions? More questions? I think we've nagged you enough during the explanation. So, any other comments? Thanks very much.